What if you could solve the vast majority of array problems you see in coding interviews with just a handful of core patterns? Well, that's exactly the idea we're going to break down right now.
It's a pretty bold claim, isn't it? The idea that by just mastering 10 fundamental concepts, you could be ready for 80% of the array questions that come your way. I mean, sounds almost too good to be true.
But you know what? After looking at years and years of interview questions, the data really does back it up. These patterns are everywhere. So let's not waste any time. Let's dive in and start building our playbook.
Okay, first up, we're going to focus on patterns that are all about what's happening inside a continuous chunk of an array. Any problem that deals with subarrays, these are going to be your go-to tools.
First on the list is the prefix sum. The easiest way to think about this is like keeping a running tally. You do one pass up front to calculate the total sum up to every single point in the array. And once you've done that work, finding the sum of any slice is instantaneous. It's just one subtraction, giving you a constant time lookup. It's an absolutely incredible trade-off.
Now, what if we want to give that prefix sum a little power-up? Well, if we pair it with a hash map, we can suddenly do some amazing things. As we calculate our running sums, we store them in the map. This lets us check in a flash if we've ever seen a sum that would give us our target k. This little combo is a game changer. It even handles negative numbers perfectly, and the whole thing still runs in linear time.
Okay, next up is the sliding window. I want you to literally picture a ruler that you're sliding over the array. That's the core idea. It's this dynamic little window that grows by pulling in elements from the right and shrinks by dropping elements from the left, all while trying to maintain some kind of rule or constraint.
And really, there are two main flavors of this. You've got your fixed size windows, which are pretty straightforward, and then you have the more interesting variable size windows. Now here's a super important tip. For those variable windows that are based on a sum, the logic almost always requires the numbers in the array to be non-negative. That's a common stumbling block.
Oh, I absolutely love this next analogy. This is for a pattern called Kadane's algorithm. Just think of your current running sum as an energy meter. As you move through the array, the meter goes up or down. But here's the key. The second your energy drops below 0, it can't possibly help you reach a new maximum sum. So what do? You just reset it to 0 and start fresh.
That one simple energy meter rule is all it takes for Kadane's algorithm to find the absolute maximum sum of any contiguous subarray. And it does it in a single pass, using basically no extra memory. So from now on, if you see a problem that mentions max profit or max sum, your brain should just scream Kadane's.
All right, let's switch gears a little. We're now going to look at patterns that are all about using the order and the relative position of elements to unlock really efficient solutions.
And the two-pointers technique is the perfect example of this. So picture a sorted array. This is key, it has to be sorted. You put one pointer at the very beginning and another at the very end. Then you just start moving them toward each other, like you're pinching inward. If the sum of your two elements is too small, you nudge the left pointer forward. If it's too big, you nudge the right pointer back. It is such an elegant way to find pairs.
Okay, this next one is a huge tip. If you're in an interview and the problem asks you to find the next greater element or the next smaller element for every single item in an array, that is a massive, flashing neon sign telling you to use a monotonic stack. It is the perfect tool for that specific job.
Now the logic might sound a little weird at first, but I promise it's really just a simple little dance. So let's walk through it. First, you look at the next element in your array. Then you look at what's on top of your stack. If this new element is bigger, you pop the smaller one off the stack because you just found its next greater element. You keep doing that until the stack is empty or the top element is bigger. And then, finally, you push the index of your new element onto the stack. That's the whole routine.
And of course, we have to talk about binary search. It's the absolute foundation of searching on sorted data, right? You look at the middle element, and with just one comparison, you get to throw away half of the entire search space. That's what gives it that lightning-fast logarithmic speed. But here's the thing about interviews. You're almost never going to be asked to write a vanilla binary search. Instead, you're going to see one of these variations, finding the very first or very last time a number shows up, or finding the correct insertion point, which we call lower and upper bounds. Getting comfortable with these subtle tweaks is what really matters.
Okay, for our final group of patterns, we're going to zoom out. We're going to look at ways to manage and manipulate entire segments or partitions of an array all at once.
And merging intervals is a perfect example.
The game plan here is super methodical. Step 1, and this is non-negotiable, you have to sort all of your intervals by their start time. Once that's done, the rest is easy. You just walk through the lists, and if the current interval overlaps with the last one you saved, you just merge them together. If it doesn't overlap, you add it as a new separate interval. It's that initial sort that makes the whole thing work.
Here's another one of those trigger phrases for you. If a problem describes a scenario where you have to perform tons of range updates, like add 5 to every element from index 100 to 1000, but you only care about the final state of the array at the very end, your mind should immediately jump to the difference array.
So how does this magic work? Well, instead of inefficiently looping through the range and adding 2 to every single element, you just make 2 tiny updates to a separate difference array. You add 2 at the start index, and you subtract 2 one spot after the end index. Then you can do thousands of these cheap updates, and only at the very end, you run a single prefix sum on that diff array, and it magically reconstructs the correct final array. It's brilliant.
And finally, we have quick select. So imagine you've got this massive, completely unsorted array, and your task is to find the 10th smallest element. Sorting the entire array would work, but it's massive overkill. Quick select is much smarter. It partitions the array and then cleverly figures out which side the 10th element must be on, and only looks there. On average, this brings the solution down to linear time.
Phew! Okay, we have covered all the individual patterns. Now it's time to put it all together. Let's build that practical playbook that you can actually use in your next interview.
All right, this slide right here, this is the whole thing in a nutshell. This is the cheat sheet. It's the mental map that connects the problem description directly to the best tool for the job. You hear max subarray sum, you think Kadani's. You hear next greater element, you think monotonic stack. Kth smallest, that's quick select. Internalizing these connections will save you so much time and stress.
And finally, remember that knowing the pattern is only half the battle. You have to communicate it effectively. So as you're coding, actually say, okay, for this, I think the sliding window pattern is a great fit. Talk about its rules. Talk about the constraints like needing sorted data or non-negative numbers. And always mention the time and space complexity and call out the edge cases. This is what shows your interviewer that you don't just know the answer, you truly understand the solution.
So, there you have it. We've built the playbook, we've got the cheat sheet, and we know how to communicate it. The only question left is, which one of these powerful patterns are you going to go and master first?